So welcome back everybody to your fourth lesson for the chemistry unit. This is on Bohr's theory specifically and periodic table trends and patterns. So to begin with, starting with Bohr's theory of the atom, which is page 87 in your notes. When atoms absorb electrical energy or are heated up, they emit light energy. Each element emits a unique pattern of wavelengths or color. Bohr developed a theory about electron arrangements to explain these observations. So this is essentially how the Bohr model came to be as a way to explain these different light observations. So you can see to the right-hand side there, there are bands of colors. These represent different wavelengths of lights emitted by these particular elements. You don't have to worry about memorizing or recognizing these bands. This is just to give you an idea that each element emits a unique pattern of wavelengths of light and color when you look at it through a spectroscope. So Bohr's theory continued. Electrons are located in defined shells or energy levels around the nucleus. When atoms are heated up, electrons are bounced up a shell. When atoms are cooled, the electrons emit light energy as they fall back into their original shell. So this is just theory and background. Don't stress too much about the details of this. So the shells themselves you do need to know. And then if we look back at the previous slide, you can see that there's a central dark spot surrounded by 3 rings. And in that first ring outside of the nucleus, you can see that there are 2 electrons, and then the second ring contains 1. So this brings us to our next slide here. Electron shells, so regions surrounding the nucleus, are called shells. The first shell holds up to 2 electrons. The second shell holds up to 8 electrons. The third shell holds another 8 electrons. And the fourth shell can hold up to 18 electrons. So 2, 8, 8, 18. So this is something that you will need to memorize and need to know. So you will be expected to be able to draw the Bohr models for the first 18 elements. So now we're going to touch on periodic table review. So you were introduced to the periodic table, I believe it was on Friday, and yesterday we covered getting you to start thinking about different trends. So the periodic table was originally disorganized by Dmitry Mendeleev based on the easily observable physical and chemical properties of elements. The arrangement of electrons in shells explains the patterns we see in Mendeleev's periodic table. Mendeleev arranged elements based on physical and chemical properties of the elements. Over 45 years later, Bohr's discoveries of these arrangements of electrons explained those physical and chemical properties. So even as we're discovering more elements, they are fitting within the trends that Mendeleev discovered and pointed out. So the right-hand image is just an overview of the periodic table. You'll notice that there are different colors pointed out. So you have in purple is the alkali metals, then we have the blue is called the alkali earth metals, then the yellow are called transition metals. The brownish color that's kind of between the green and the orange are known as metalloids, and then you have your non-metals on the right-hand side. The yellow-ish kind of color, not the middle yellow, but the far right, those are known as the halogens, and then the light purplish blue are the noble gases. So we're going to go into a little bit more detail into these later. So elements in each row are called, which is also known as a period, in a periodic table have a new shell. So as you're moving down the periodic table in rows, a new shell is added as you move down to each row. The elements in the first row have one shell, so this would be like hydrogen or helium. There are only two elements in the first row because the first shell can only hold 2 electrons. So hydrogen has 1 electron, helium has 2 electrons. As elements are added across these rows, also known as periods, electrons are added to the shells. Once a shell is full, a new row begins. So why is the periodic table of elements called periodic? The properties of elements are periodic, or regularly repeating. The elements in each column, so this is going up and down, are known as a family or a group. These have the same number of electrons in their outer shell. So this is what's known as the valence electrons. We'll get into these later. Valence electrons are the outer shell, is called the valence shell, and the electrons in the outer shell are called valence electrons. Valence electrons determine the reactivity of an element and which elements will combine to form what we call compounds. So if you look at the first family, so this is hydrogen, lithium, sodium, potassium, rubidium, and cesium, they all have one electron in their valence shell. And then you'll notice as we're moving across to family 2, we see 2 electrons. Family 13 has 3 electrons, family 14, 4 electrons, family 15, 5 electrons, family 16, 6 electrons, family 17 has 7 valence electrons, and then family 18, which are your noble gases, contain 8 valence electrons, meaning that there is a completely full outer shell. So this is helium, neon, argon. That K is in the wrong spot, sorry. So there is an error in family 18 where you see the K. That should be Kr, which is krypton. And then xenon is your last one there. So we have 4 famous families, which are important to know. So the alkali metals, which are the most left-hand column or family, and they have 1 valence electron. These are super reactive because they only need to lose 1 electron to obtain a complete valence shell. Next over, moving to the right, is your second family, the alkaline earth metals, which have 2 valence electrons. They want to lose 2 electrons to obtain a stable valence shell. They are less reactive than alkali metals. Then we're going to go all the way across the periodic table to the far right, and the second most right column family are known as the halogens. So they have 7 valence electrons. So this is family 17. So 7 valence electrons. They are very reactive because they only need to gain 1 electron to obtain a stable valence shell. Our last family in family 18 are the noble gases, and these are completely unreactive because they have a full valence shell. And noble is actually spelt wrong on this slide. It should be N-O-B-L-E gases. So I'm just going to walk you through understanding how to read the periodic table. You may want to have that website I sent you yesterday. So I think it's just ptable.com in front of you. But essentially, our modern periodic table includes information and is organized as Mendeleev had predicted. So if you look at the number 22 in the top left-hand corner, this is what is known as your atomic number. An atomic number is actually related to the number of protons that a particular element has. So this number never changes. It identifies the element as the particular element. So titanium has 22 protons, and this is its atomic number. Then below that, the Ti is your element symbol. So you'll notice that it's a capital letter followed by a lowercase letter. And then we have the element name, which is titanium in this case. At the very bottom middle is your atomic mass. This is always rounded to, or usually is rounded to a 10th decimal place. And this is the sum of, it's actually an average, but it's the sum of protons and neutrons together that makes up this number. So lastly, in the top right-hand corner, we see ion charge or charges. In this case, titanium is what is known as multivalent, meaning it has 2 ion charges. So ion charges. Atoms become charged when they gain or lose electrons. Any atom with a charge is called an ion. So whether or not it's a positive charge or a negative charge, it is an ion. If an atom gains electrons, it will have a negative ion charge. This is what's called an anion. These are found on the right-hand side of the periodic table. So it's important that you know that the anions are on the right-hand side. If an atom loses electrons, it will have a positive ion charge, also known as a cation, found on the left-hand side of the periodic table. If this helps you, somebody told me this at some point during my educational career, cats have paws, can help you remember that cations are positive. For all elements, the number of protons is equal to the atomic number, as I pointed out before. The number of electrons is equal to the number of protons, which is equal to the atomic number. The number of neutrons is equal to the mass number minus the atomic number. And this is because it's made up of protons and neutrons. That's what makes up the mass of the element. Now, one thing to point out, be aware that this is for elements. This is not for ions, because the electron number will vary if you're dealing with an ion. But for elements, the number of electrons will equal the number of protons, which is equal to the atomic number. Always round atomic mass to the nearest whole number to find the mass number. On the periodic table, we'll notice that it's a decimal, but you will be rounding to the whole number to find the mass number. So I would like you to take a moment, pause here, and complete the following questions. So these are from your notes. I will be posting an answer key later for this particular slide. So the last thing I'm going to cover for today is standard notation. So standard atomic notation is a shorthand way scientists use to communicate important information about an atom or ion of each element. So for example, let's work with the element potassium. So potassium has a symbol on the periodic table, which is K, capital K. And then the mass number, if we read the periodic table, is 39.1. So we're going to round that to 39. And then the atomic number is 19. So when we put this together, the standard notation looks like capital K with a little 39, and then the 19 goes at the bottom. So this is standard notation. I'm just going to go back to this slide to give you some information to help you get started here. So the name of the element here is scandium. The symbol is capital S and a lowercase c. The atomic number here is 21, which would mean we have 21 protons. The number of electrons, because we're dealing with an element, is also 21. The charge is +3, which would mean we have lost 3 electrons, which is symbolized by E-. So, and the number of electrons in the ion we can calculate. For number of neutrons first, if we round this up to 45, which is the mass, minus the number of protons, which is 21, you end up with a total of 24 neutrons. For electrons in the ion, which remember we have lost 3 electrons, it's going to be 21 atomic number minus 3, which gives us a total of 18 electrons. So jumping back to standard notation for ions now, the standard notation for ions is exactly the same as for atoms of an element. So write the symbol, which now we're dealing with potassium ion, it's still K. The mass number is the same, which is 39. And then the atomic number is below, and this is 19. And then we're going to write the ion charge above and to the right of the symbol. So in this case, potassium has a charge of 3+. So it's going to be K, capitalized, 39, 19, 3+. Okay. The last thing that I'm going to cover with you is just a quick little introduction to Bohr models. I'll be reviewing this again with you tomorrow. But okay, so how we draw a Bohr model. So for example, let's start with lithium because it's an easy one. We draw our nucleus, and if we look at the atomic number, is 3. And remember that this is equal to protons. And we shorten protons to a lowercase p. Electrons in the atom, also 3, because it's an atom, it's not an ion. And then our neutrons, we figure out by taking the mass, which is rounded to 7, subtracted by the atomic number, which is 3, to give us a total of 4 neutrons, which we symbolize as a N. So when we set this up, we have in the nucleus, it's made up of 3 protons and 4 neutrons. And then we have a ring around it. And the first shell, which is what this outer ring represents, can hold 2 electrons. So 2 of our 3 electrons are going in this shell. And then you have 1 electron left over, which you can place on the next shell. So this is just a quick introduction on how to draw the Bohr model for lithium. It is a good idea as well, which I did forget to do, to include the element within just to keep track of it as well. Okay, so that is going to be it for today's lesson on chemistry. Please follow the schedule for information on which assignments to work on now.